So this talk will be about rod-coil diblock copolymers. And in fact, I forgot to include the word liquid crystals into the title. But my very interest in the topic is related to liquid crystals, and it stems from liquid crystals. Because the key word here is rod. So these are the polymers, which are composed of long macromolecules, and these macromolecules contain a rod-like part and a flexible part. So in this sense, they are exaggerated liquid crystal molecules, because we know that liquid crystal molecules have a rigid core and flexible tails. Just in this case, the flexible tail is very long, and so it can be treated approximately as an ideal Gaussian chain. And so then it is interesting, of course, to see to what extent we can use the existing molecular theory of liquid crystals to describe these systems, and how this can be combined with the existing polymer theory. So this is a kind of the hybrid theory between the two. And this has been done with my old coworker, Maxim Gorkunov from Russian Academy of Sciences. So just if we look at very simple systems, so just coil-coil diblock copolymers. So the difference is that the macromolecule here is composed of two flexible parts, but of different origin, and the monomers in the two parts, they repel each other. And this is a key feature. So because of this repulsion, they form a whole bunch of interesting phases, so depending on the concentration, starting from micelles, then into lamellar of various kinds, hexagonal phases, cubic phases of different symmetry, and so on and so forth. So remarkably rich phase behavior in these simple systems. And of course here, everything depends on the fraction of one component. So if we take, say, the component A and start to increase its smaller fraction, then we go along all these phases, starting from spheres, then cylinders, which makes hexagonal phase, then gyroid, lamellar phases, and then in the same order backward. And so this is actually the theoretical phase diagram, which has been obtained by Leibler many years ago, which represents most of these phases. So here you have the fraction of one of the components, and here you have the parameter which specifies the repulsion between the monomers of different kind. And so we will return to all these things. But actually, what I'm going to describe are the rod-coil diblock copolymers. So they have this rod part, which is also composed of monomers, but they are rigidly bound together, and a long flexible tail. And if you look at the typical phase diagrams, the experimental phase diagrams of these systems, then they resemble those of liquid crystals, in effect. Because you have, for example, if you look at what experimentalists do, they can control temperature, and they can control the fraction of the coil just by synthesis. But it's much more difficult, of course, to control the parameter, the repulsion parameter, the so-called Flory-Higgins parameter in the theory of polymers. And so here you have just, if you fix some fraction, and then you go down with temperature, then you start with isotropic into the nematic, and then into the lamellar phase. And the lamellar phase is actually the analog of the smectic A phase. It has exactly the same symmetry. And if you, in some materials, so the phase diagram is slightly more complicated, so there is also a hexagonal phase, which sits somewhere here at low temperatures, and which is not present normally in usual conventional liquid crystals, except for complicated smectics. Okay, and so, but the difference here is determined by the fact that in the case of these rod-coil block copolymers, there are two factors which promote layering, which promote these layered phases, just periodic phases. So, of course, the primary one is just microphase separation, typical for coil-coil polymers, because we also find lamellar phases and similar phases in coil-coil polymers without any liquid crystal order. So this microphase separation and the fact that the two parts of the macromolecule are linked together, this creates instability at a certain wave vector, and as a result there is periodic structure. simple lamella, more complicated hexagonal, or even more complicated cubic one with several density waves. And in addition, if we have rods, then of course rods interact. There is a liquid crystal type interaction between rods, and this brings also all types of liquid crystal effects, like the tendency towards smectic ordering. So the longer are the rods in conventional liquid crystals, the stronger is the tendency to form smectic phases. And so now these two effects, microphase separation and smectic ordering, they come together. And as a result, the lamellar phase generally appears the most stable and the most common phase in these systems. And nematic phase is actually quite rare, although it happens. And so then now of course, it would be interesting to see how we can describe both mechanisms in this case. So this is another cartoon, so biochem model, as we call it, of the rod-coil copolymer macromolecule. And so also that the main content of what I'm going to tell has been recently published, but not everything. And now the goal of what we're going to do is to create the so-called free energy functional. Because in the title, we see that this is a density functional approach to the molecular theory of these systems. So we need density functional, which in this case means that we want to express the free energy as a functional of the two number densities. These are the number densities of rod and coil segments. And so I would just try to take this opportunity to discuss how this can be done in general, because the whole procedure and the density functional approach are, of course, much more general than the theory of this type of polymers, or even the theory of polymers at all. So it can be applied and has been applied to many different soft matter systems. And so if we just try to start with the first principles, so we can write down the well-known expression for the Gibbs free energy, right, in the statistical mechanics. And this Gibbs free energy is the functional of the external field, which may be spatially dependent. And also, if we want to fix the state of our system, we create the so-called auxiliary field, which is just a fictitious field, which is used just to control density. And then this auxiliary field may depend also on the position and on orientation, which actually happens, like, for example, external electric field or magnetic field has orientation. So generally, this U depends on all variables, both translational and orientational degrees of freedom. And so that's the Gibbs free energy. And then, as we know in thermodynamics, the thermodynamic potentials, they come in pairs. There is a pair of conjugated thermodynamic potentials, like, for example, Gibbs free energy and Helmholtz free energy. And so the conjugated potential then, in the general case, depends on the equilibrium density in the system. Because if you can see here in the Hamiltonian, in the Gibbs free energy, there is a coupling between external field and the microscopic number density. And the macroscopic number density can be expressed in this way for point-like particles, for simplicity, with translational and orientational degrees of freedom. And on the macroscopic level, the conjugated thermodynamic variables are the density and the external field in the general sense. And so then there is a generalized Legendre transformation, well known in thermodynamics, which establishes a relationship between two conjugated thermodynamic potentials. And so that's the general way how we proceed from the free energy as a function of external field, which we can, in principle, measure, or in principle, calculate using Gibbs free energy, to the free energy which depends on the density, and we cannot directly control density inside the materials. That's the problem. So there is no general formula for this free energy. And so this thing has to be derived somehow using some approximations. But without this, we cannot develop any theory of any phase transition, because phase transition between any two phases corresponds to the change, qualitative change of the equilibrium density, because the symmetry changes. And so if we want the phase diagram, for example, of liquid crystals or of these rod-coil diagrams, we do need this free energy. And so now, of course, that's a very general thing. In this case, the equilibrium density, of course, is just the functional derivative of free energy with respect to the external field. And that's all nice, but these are two general formulae. It doesn't give us any method how to calculate it. And so I'm going now to discuss two different methods, because in principle, there are more than two, but I'm just comparing two. And so there are two different approaches to this. The first approach is free energy expansion in this or that sort. And the second approach is the density functional theory. And so we will start with free energy expansion, because free energy expansion should be used when we want to derive something like Landau-Desjardins theories of phase transitions in terms of various order parameters. And so we can briefly discuss how, in principle, this can be achieved more or less systematic way from the physics point of view. So if we just take our Gibbs free energy as a function of external field, then we can formally expand it in powers of the external field. And then the coefficients, we're interested in the coefficients, of course. And the coefficients are the so-called density correlation functions. So this is delta rho is the deviation of the actual density, which is generally inhomogeneous, and the average density of a certain type of molecules. And so the quadratic coefficient is the two-body density correlation function. The cubic coefficient is a three-body, and so on and so forth. So this is very nice and pretty. And then we can, of course, differentiate this free energy with respect to the external field and get an analogous expansion of the equilibrium density, again, in powers of the external field with the same coefficients here. And so now the crucial step is that we can invert this series, in principle, assuming that everything converges and other things which physicists do not bother about. And so, but at least in some cases, we believe that this can be done. And then we can use it to expand these external potentials in powers of the equilibrium density and substitute back into the free energy. And in this way, we obtain the expansion of the free energy in terms of these equilibrium densities, more exactly deviation from the average, but it doesn't matter much. And so now the interesting thing is to evaluate these coefficients. So these coefficients are given in general by a very complicated formula, but these formula exist for every finite order. You can write an expression. But a particular simple expression is for the quadratic coefficient, which is simply 1 over the corresponding density correlation function. And so that's in principle a general expression for the quadratic term in this generalized Landau-Desjardins expansion. But here we have density, right? And Landau-Desjardins expansion is normally written in terms of order parameters. So the next step in this approach is to express density, expand density in order parameters, right? Because density may be quite a complicated function of the order parameters. And for example, in the theory of coil-coil polymers developed by Leibler and in the Desjardins school, that's actually how it is done. So I more or less follow this logic. And then the final approximation here is to assume for simplicity that this density, equilibrium density, is represented by just a single mode, a single harmonic. So there's only one wave vector involved, which corresponds to the periodicity of the phase. And then you have just an amplitude of this harmonic, which is a translational order parameter, lowest order translational order parameter. So in principle, you can, of course, write many of these terms here and introduce a set of translational order parameters. But this is generally not done, because even with this, the theory is computationally quite complicated. But this is, of course, a very weak point of this approach, because we understand that at low temperatures or at strong separation, we have well-defined layers, some of them filled with flexible, say even block A and block B, composed of different parts of the macromolecule. And so this is definitely not a cosine wave. It's something strongly nonlinear. And so as a result, this approach, even though it is extremely general, it can be applied only close to the spinodal line, so close to the transition into the disordered phase or at high temperatures. And then also, because polymers are very incompressible, so Dejean has introduced this incompressibility condition, which is used in all existing theories of polymers, so that the average density is approximately constant. So that's one approach, when we develop the density functional in the form of expansion in powers of density. And the second approach is completely different. So in the second approach, let us assume that we have our free energy F, which is the functional of equilibrium density. We do not know its structure, but we can generally split it into two parts, the so-called ideal gas part, or just the entropy of the non-interacting monomers. And then the second is the functional H, which is unknown. It's also the functional of the density. But what is nice about this functional, that the functional derivatives of this functional are known. So that's the content of the general classical density functional theory, so that we're particularly interested in the second partial derivative, because the first partial derivative just vanishes in the equilibrium state. And so we have this second partial derivative, which is expressed in terms of the so-called pair correlation function. And this is not just a pair correlation function, but the direct pair correlation function. So it depends, so X here combines all variables, including translational and orientational. And now, this is very much different from the density-density correlation functions, which we had in the expansion of the free energy. So we need to establish some relationship. And this relationship can be indeed established. So firstly, there exists the following exact Einstein-Zernike equation, which establishes a relationship between the so-called full pair correlation function and the direct pair correlation function. And so the full pair correlation function describes all correlations between the molecules 1 and 2. And the direct pair correlation function is something like the short-range part. That's why it is called direct. So the full correlations are equal to the direct correlations plus correlations via the third particle. So we had two particles, 1 and 2, and then we take any other third particle, and there is indirect correlation via third particle, which goes to infinity in principle, because then there is a fourth particle, and so on and so forth. And so this term determines the long tail of the correlation function, and while this direct correlation function is short range, so it decays on the molecular size, approximately. And then finally, if we want a formal definition of this full pair correlation function, then it is given by this standard formula in the statistical mechanics, where this is the two-particle distribution function, which simply tells us the probability to find a particle 1 in the state x1 and the particle 2 in the state x2. And so then this two-body distribution function at large interparticle distance, of course, should go to the product of two one-particle distributions, because all correlations should decay sooner or later. And then the two orientations and positions of the two very distant particles must be independent. And so that's why there is one here, which is abstracted. And then all the rest is called the full correlation function. And so now we have the relationship between all of these things. And then later on, when we develop a theory, we would, of course, have to establish a rigorous relationship between the correlations used in the expansion and the correlations used in the density functional approach. So now, how do we obtain the approximate free energy using density functional theory? So, of course, we cannot calculate this functional. But what we can do, we can take into consideration that we know the second derivative, and then we can expand the free energy around the reference state. But because we do not expand the full free energy, we expand only that functional H. We keep this entropy as it is, so it is there. We only expand H. And so here we have this direct correlation functions. And the second term is quadratic in the deviations of the density from the density in the reference state. And so usually people use isotropic phase as the reference phase, of course. And then in this case, the first term here is just the free energy of the isotropic phase, which we're not interested in. So we're only interested in extras. And here it is already written for the case of a two-component system, so our rod-coil polymers. So the rho C is the density of coil monomers, and rho I is the density of rod monomers. And here we have these metrics of direct correlation functions, so coil-coil, rod-coil, and rod-coil. And again, so that's just a general thing. And now the question is, and what is this? Can we calculate this direct correlation function? Because in the general case, that's just impossible. Even if you take the system of ellipsoids, it's impossible to write down anything analytical about it. So one has to do some approximations. And now I just note that if the expansion of the free energy in terms of density can be used to derive any existing Landau-de Gennes theory, exactly in the same way, this expression can be used to derive any existing mean field theory, virtually for any system. And this is done in the following way. So we need some approximation for this correlation function. And if we look at the polymers, then we say that there are strong correlations between monomers within the chain, which we cannot neglect. And then there are relatively weak correlations in monomers and neighboring chains, which we just blindly neglect. And this is generally called the mean field approximation. And so this means that we approximate our correlation function as C0 within one chain, and then the interactions between chains which we like to take into account. And here, of course, there are models. So we adopt just a standard Flory-Higgins approach with later works, where people take into account only two types of interactions. So effective repulsion between rod and coil monomers, and the Meyer-Sauper type orientational interaction, which would account for the orientational order in this system. So in this sense, that's just a minimum model which combines the properties of polymers and the properties of liquid crystals. And so we will return later to this thing, because we would have to calculate this. And this can be calculated actually using the existing results of the polymer theory. So now if we try to summarize it, now our approximate or model free energy would look like this. So that's the isotropic and free energy of the isotropic phase, then orientational and translational entropy of monomers in the standard form, then effective repulsion between rod and coil monomers, then monomer-monomer correlations within one single chain, or formally just in the system of non-interacting chains. And then the orientational interaction between rods, which is taken in the simplest Meyer-Sauper form. And so now what we need here, we need to determine these densities, right? Sorry?
Just a quick question. So the interaction between the tail and the rod are in monomer member?
Yeah, the thing is that, of course, there are more interactions here, but there are plenty of interactions between different chains, which are not taken into account here. And that's not only that I'm not taking it, but I'm trying to follow the existing polymer theory, which just tries to make as simple model as possible, because there are plenty of other things. For example, this Meyer-Sauper interaction is, frankly speaking, very much incorrect, because the real interaction between rods is not only a coupling between long axes. It involves the orientation of the rod with respect to the intermolecular vector, right? And in the nematic phase, that's fine. You can average it over all orientations because that's, there is no positional order. But in the smectic phase or in the lamellar phase, this is a very poor approximation. So there are more serious things here which have been neglected. Of course, there are, say, repulsion between like monomers, but they do not change anything. They just shift the free energy. Okay, and so now the difference with expansion is that we do not expand the whole free energy, and so as a result, there is a nonlinear part in density here, which is the entropy. And so if we minimize this free energy, or more exactly like physicists do, we just set the functional derivative of this functional equal to 0, which should be valid at the extremum, which we assume to be a minimum. And so then in this case, one obtains the self-consistent equations for the densities. And that's the difference with the expansion. So we have them in the Boltzmann form. So this is already a familiar type of the expressions from a typical mean field theory, where you have these Boltzmann exponents with effective mean field potentials. But in fact, that's an integral equation for the density, because density sits also in these integrals. And integrals with the corresponding correlation functions or interactions between chains, they contribute to the so-called effective mean field potentials. So in this form, again, that's quite general, and it can also be reduced to the expansion. So formally, we can now expand that and get something similar to the expansion in density, which was obtained previously. But so this looks like an effective summation of the infinite series under some assumptions, so that what we neglect here, we neglect many body correlations, because we only keep the quadratic term on the expansion of the free energy, and the next term is proportional to the third rank direct correlation function. Well, yeah, this can be important, but still it doesn't change things qualitatively. Okay, and so now, yes, if we just, okay, so we take into account so that we have expressed our densities, at least in principle, via the integral equations in terms of the direct correlation functions. But we still need to calculate these direct correlation functions for the chains. And in the polymer theory, people calculate density-density correlation functions. So that's something different. And we need to establish a relationship, and this can be done. So again, if we start with a general Ornstein-Zernike equation for a two-component system, so there are two species here, eta and nu, but it looks similar, then this equation can be solved in the matrix form and in the Fourier representation. And because it's just the equation for one chain, so there's just orientation of the rod in this chain, so that's the solution here. And then we take into account, again, the rigorous expression between density-density correlation function and the full pair correlation function. And if we exclude this full correlation function from these two equations, then we obtain this relatively simple relationship between direct correlation functions of the two-component system and the density-density correlation function. So this is just the elements of the inverse matrix of J, the inverse matrix of density-density correlation functions. And then now to check that, we have used these direct correlation functions just in the theory of coil-coil diblock copolymers, which is well developed, in order to obtain the first few terms of the expansion obtained by Leibler. So the quadratic term then, of course, should be correct, and it is indeed exactly the same. Then in other terms, of course, there is a deviation, but this reproduces exactly the spinodal line compared to the formal expansion. But in the Leibler's theory, again, the higher order correlation functions, even in the theory of polymers, cannot be calculated exactly. So there are other approximations which are used. So this looks reasonable. And so now let us discuss these density-density correlations a little bit more. So there are three of them. So firstly, there are correlations within one rod, which is simple. And then there are correlations within the flexible chain. And these correlations are the same as in the standard theory of flexible polymers. So if we assume that this is a Gaussian chain, then we can just input the results which have been obtained. So for the flexible molecules, this has been obtained by Leibler in 1980. And then there are also mixed correlations between rod and coil monomers, so they can be expressed as a product of two terms. So here, these Fi and Fc are the fractions of rods and coils, n is the length of the chain, and then, so this function depends on x, and x is the function of the wave vector, length of the chain, and a is the radius of the monomer. And then the second factor here depends on y, and y is orientationally dependent, as it should be, because we have a rod with a unit vector a along the rod, and then it is sensitive to the coupling between the unit vector k, unit wave vector k, and the orientation of the rod. So generally, these rod-coil correlation functions are orientationally dependent, and this is quite important because this contributes to the liquid crystal ordering. This is actually a coupling between the microphase separation effect, which creates this wave vector primarily, and then the orientational order, which is partly induced by this part of the correlation function, on top of the standard effect determined by the Myers-Alpha interaction. Okay, so now, oh, sorry. What is it? So now we can also do the last bit. So we expand our correlation function, our direct correlation functions, which depend on density-density correlation functions, which depend on the orientation. So we can expand them in Legendre polynomials, again taking only the first interesting term, which contains the second Legendre polynomial, because our interaction is limited to the P2 term in the Myers-Alpha. And so in this, then if we use that, and then finally if we expand the all mean field potentials in Fourier, then we get these approximate expressions for the densities. So for the densities of coil monomers and for the densities of rod monomers. And they are actually so these coefficients can be calculated. So all these coefficients calculated from the density-density correlation functions, which are taken from the polymer theory, and these quantities underlined by red are the order parameters of the system. And these order parameters are, so they are familiar to the people who worked in the theory of liquid crystal, of smectic liquid crystals. So there are three actually order parameters. And so the first is the standard orientational nematic order parameter with just the average of P2. Then there is a standard translational order parameter, or more exactly, there are two of them for rods and for coils, and they're just averages of the cosine. And then there is a mixed order parameter, so-called orientational translational order parameter, which is the average of the product of cosine and P2. And in the case of polymers, it's quite important because what we have in polymers, because of the microphase separation, we have orientational density wave, which normally appears. In particular, when there is no nematic phase, when the system directly goes from the isotropic phase into the lamella, then two types of order appear simultaneously. And as a result, this is a very important order parameter here. And so, but now there is additional things. So as I mentioned already, so de Gennes introduced this incompressibility condition, which can be written approximately in terms of the order parameters and fractions of rod and coil monomers in this form. And then what is normally done in the existing Landau-de Gennes theory of these systems? So people just substitute this relationship into the free energy expansion, and then at the end they get a nice expansion in terms of one order parameter, and they can compare different phases and to perform stable and standard analysis of this. But in fact we cannot do that, because we understand that this condition in the framework of the molecular statistical theory should be taken into account using the formalism of Lagrange multipliers. So we need to add to the free energy this term with Lagrange multiplier, which has the same form as here, but these order parameters are expressed explicitly as averages. So that's also the functional of the two densities. I do not know. Yeah. And so now if we take this into account, then we have these slightly corrected expressions for the densities of rod and coil monomers. So there are additional factors which contain, additional factors which contain these terms with the Lagrange multipliers. And now these Lagrange multipliers must be determined numerically. Because from now on, of course, that's impossible to do anything analytically with this. So one has to minimize this free energy numerically, taking into account this constraint. And so this means that there is an integral equation for this Lagrange multiplier, which sits in these two densities. And technically, this should be solved numerically at every step of minimization. And then we minimize the free energy numerically directly, determining lambda at every step in order to find the order parameters and then to compare the free energies of different phases. And in this case, of course, you get as many phases as you take into account, because in each phase there is slightly different symmetry and different densities. So you have to write separate expression for the free energy for every phase. No, that's a usual thing. And then to compare the free energies to get the phase diagram. And so these are just the phase diagrams which have been obtained using two different methods. So the first method is the self-consistent theory with Lagrange multipliers. And the second diagram, just direct minimization when we substitute this relationship, like it is done in the phenomenological theory. And then we see that at least if you are away from the transition in the statistical theory, this is quite poor. So these two phase diagrams differ significantly. So in this case, you have these three phases. So isotropic, nematic, lamellar phase, so relatively narrow part between isotropic and lamella goes all the way down to the left corner. But of course, if you just obtain this phase diagram, you do not, it's not obvious that there is something incorrect here or something inconsistent. But this becomes, okay, you can see it like this. Okay, so maybe. Okay, thank you. Yeah, so again, here are the order parameters. So all order parameters of the system calculated using self-consistent theory in different phases and using this simplified minimization procedure. And here you can see what goes wrong. Because, for example, this translational order parameter exceeds 1. And the reason is that if you simply use this without correct formalism of Lagrange multipliers, then the self-consistency equations for the order parameters are violated. And so just non-physical results are obtained. And so this method also enables one to determine order parameter profiles. And finally, a very recent result, we have generalized this to the case of the hexagonal phase. And so now there is a more complete phase diagram which contains all phases which are generally observed in rod-coil systems, also with the corresponding order parameter profiles, and the final picture with the spatial distribution of density and order parameter in the hexagonal phase. And so thank you for your attention.
Thank you very much. Any question or comment? Yes.
You mentioned that for different symmetries you need a different free energy.
Yes.
I didn't understand that because usually, for example, in the block copolymers, the self-consistent field theory, when you so the phase diagram that you showed at the beginning.
Yes, the line.
That's the same. Yeah, there's the same free energy. You just change the parameter. You just change the length of the coil, or the segregation parameter, right? And then you get the different phases.
No, you see that they look the same, because if, so I can show you, for example, no, well, I can tell this in words. So you start with a general expansion in terms of density. Yeah. And then you ask for yourself, what is the equilibrium density, say, in the lamellar phase? That's one density wave. And then what is the density in the hexagonal phase? There are three equivalent density waves. And so you need to explicitly include three density waves into the free energy expansion, and you get slightly different formula. Otherwise, the free energies would be the same. You wouldn't have a transition between one phase and another. And now imagine that you have orientational order in one phase and no orientational order in another phase. So of course the free energies would be different, because they just depend on the different set of order parameters. And there is a unique set of order parameters for each phase, which is determined by symmetry. So that's a standard thing in liquid crystals, which have many different phases. It's the same in this Ten Brinke renders phenomenological theory of rod-coil copolymers.
Perfect. Further questions or comments? Seems not to be the case. Oh, yes, it is.
So in the sort of penultimate slide, you have these phase diagrams, and you're explaining the order parameter for the, was it the translational part, was going into an unphysical regime. So it was greater than 1. And there was, and you also had in the actual phase diagram where the pneumatic phase sort of disappeared. So everything seemed to be reasonable up to a certain temperature in both. Are these at the same temperature?
No, here, for example, everything is consistent. So here all order parameters behave nicely, and it can be shown that they approach 1 only at infinitely low temperatures. I just presented this for illustration, because even in the original paper of Leibler, he has introduced just this condition formally. And this may look okay, but if you go away from the spinodal, then order parameters will shoot and will exceed 1, which is not visible in Landau-de Gennes, because nobody takes seriously the values of order parameters which are obtained in Landau-de Gennes theory. Right, but so that's just, so you have to use Lagrange multipliers to get everything correctly, because there is a self-consistency equation for order parameters which can be derived in the formalism of Lagrange multipliers, and this prevents it from going above 1. So it can be rigorously shown that it's less than 1. And if you use this, then you mix all equations, and this, you lose this self-consistency.